Welcome to a new episode of the video series From Classical Mechanics to Cold Atoms, where I try to give you intuition on how to go from the classical to the quantum world. Let's go. In the previous episodes, we learned that the de Broglie wavelength was the right parameter to tell whether we were in the quantum regime or in the classical regime, and that by slowing down the atoms, we could go from one to the other. But by using the technique called laser cooling, we were capped and we could not cool the atoms lower than a temperature of roughly 1 microkelvin. So now we have to resort to a different kind of technique to go beyond this temperature and to go into the quantum regime. This technique is called evaporative cooling, and in order to understand it, we need to change a few of the things we were assuming before. And one of the most important ones is that instead of having a single atom, we need to resort to having many of them trapped in a certain potential with a depth equivalent to something like 20 microkelvin. Now, the atoms in this potential, in this trap, are gonna have internal energy E1, but they are gonna collide against each other all the time. If this happens, then the temperature of the system is going to be constant and it's going to have a certain energy distribution, meaning that the atoms, instead of thinking about them as hot or cold, we're going to think about them as more energetic as the ones in red or less energetic as the ones in blue. Then, depending on the trap depth, in this case 20 microkelvin, the sample is going to have a certain fixed temperature and we're going to have an energy distribution across the atoms. Then the cooling process is as follows. We initially have a bunch of atoms with a certain energy distribution at a temperature fixed by this trap depth, which is about 20 microkelvin. And then what happens is that we reduce the trap depth of this potential by roughly half. Then the more energetic atoms, the ones that can escape the trap, will do so. And because of the collisions, the sample is gonna rethermalize. So we're gonna have a lower temperature and a different energy distribution where the most energetic atoms are gonna be less energetic than the most energetic atoms that we had at the beginning. Now, if this process is repeated a few times, you can see the evolution of the temperature of the sample as a function of the number of times we reduce the trap depth, and is shown in semi-log scale. As you can see, the temperature decrease is significant with the number of times we decrease the trap depth. And now what we have to pay attention to is the relation between the distance of the atoms and the de Broglie wavelength, because at this point the de Broglie wavelength is going to become significant. Then when the two quantities, the distance and the de Broglie wavelength, become comparable, we're gonna start going into the quantum regime and a phase transition is gonna occur, which is gonna be the topic of the next and final episode.